So hi guys, my name is Praful Kumar and today I'll be recording a video for subject design and analysis of reconfigurable systems. So this is the first project that we are creating. So we'll be creating a full adder design. So for that you need to have Cortex Prime Lite Edition installed, which is free, and along with this you also need to install Questa, which is a simulation tool. But for that you have to go to Intel Licensing Center and then you have to register and generate a license file, and that license file then you add it to the software for in order to use a simulation tool. So now to create a new project, you click on file and then here you have to click on new project wizard. So since I have already opened the project, I'll just close this and show you how you can create a new project folder. So you click next here and then you have to create a working directory. So I'm gonna create a new folder here which I'm gonna call FPGA 4, and then I'll click select this folder, and for this folder you have to give a name for the project. So I'm gonna give full adder 1 bit. So I'm gonna click next, and then since I'm not adding any files, I'll just create a empty project. So you click next here and here you select the family of the device, the FPGA board, which in our case is Cyclone 5. You also select the device, which is Cyclone 5 SE mainstream in my case. So here you select the device name. So here in our case it's this device we are using, and then you click next, and then here you need not to change anything. You can just leave it as it is and you just click next, and then again you click finish. So now you just click yes here. It's gonna take a while. So now we have successfully created a project. As you can see, we have created a project called full adder 1 bit. Okay, now I'm gonna show you how you can create a schematic for full adder. So you click on file and then you click on new, and here you can choose block diagram or schematic file and click OK. Since I have already created a full adder, I'm not repeating this step. So you'll get this window. On this window, if you double click, you can see library here. You can double click on this. You can go to primitives. You can select the gates from the logic section, and for the pins you will have pin section in which you can create input output pins or bidirectional pins. Once you create the circuit, you can rename the pins by just double clicking on this and then renaming it. So that can be done by this. So the next step would be to create a HDL file using the schematic. So this is the schematic here. You double click on the schematic and then you go on to the file section, and here you can see create or update. Here you can choose create HDL design file from the current file. So it will take the gate level design schematic and it will generate a Verilog for that. So once the Verilog file has been generated, you can right click on this. You can click on add or remove files in the project, and you can navigate through the file. So as you can see, this is the created one. You can just click on this and click open. So this file will get added into the project folder. So now I'm going to show you how you can create a test bench for this design. So you double click on this, you go to processing, you can click on start, and then here you can see start test bench template writer. So this will generate a template of test bench, but you have to write all the test cases in that design. So if you can see, this is how it generates. So I have written the test cases here. It will just generate the skeleton of the test bench. So you have to write the test cases. That's something you have to remember. So the next step would be to remove the schematic. Since you already have generated the Verilog for the schematic, you can just right click on this and you can select remove file from project, and now you can set this as top level entity. You can right click on this Verilog and then you can click on set as top level entity. You can also use a shortcut which is Ctrl Shift plus V. So once you make this top level entity, you can simulate here. So as you can see, we have successfully completed the simulation with no errors. So now you can see the flow summary, in which it says it has used 2 ALMs and total number of pins are 5, which is 3 inputs and 2 outputs, A and B seen as input and C out and sum as output. And here also you can see the number of pins, resource usage. Yeah, here you can see combinational ALUTs, that is 2 that are used for the specific schematic design. So since we don't have a clock for this design, there are no clocks. So now I'm going to show you how you can get the timing analysis of this design. You select this timing analysis, go to timing analyzer, and then here you can see the report. On the custom report, let's say if you wanna see the critical path, the longest path of the circuit, you can just click on report path. It's gonna take a while and then it'll report the path, the longest path in the circuit. Okay, so it's giving me from the pin A to the output pin S. So the delay is 6.640. So this is the longest delay in the longest path delay in the circuit. So the frequency should be inverse of this, that is 1 by the time period of this, and you should be able to get the maximum frequency for that circuit. So let's say if you have the higher frequency, then the circuit might not work. So this is the highest possible frequency allowed for that circuit in order to work. So after you have created both the test bench and the design code, you can go to tools, you can click on run simulation tool, and you can select RTL simulation. So now this will open up on the Questa simulator. Yeah, so it has opened up the Questa simulator. Okay, now you click on compile, and then you select the design code. This is the simulation code and this is the test bench code. I'm gonna compile this. So as you can see, this has been successfully compiled with 0 errors and 0 warnings. You can go to the design code, that is in FPGA folder. This is the design code. So you can click compile. So this has been compiled with 0 errors and warnings. You can click done. So once you compile the design, you can see the test bench that is here. in the simulation quest full adder not be this the test bench. You right click on this, click on simulate. So now it will open the waveform window. Okay, so now you can right click on this and you can click on add wave. So this is the waveform window it has opened. Yeah, now if you can see, these are the input ports A, B, C in, C and S. This is C out and sum. So now I'll run the simulation. Yeah, now you can, if you observe, so here are the uh, output simulation of adder. Yes, and this is in picoseconds. So now I'm going to show you how you can do it for 4-bit full adder. So I have already written a code for it. So all I have to do is I have to import it into the project directory. So here I'll right click on this and I'll click add or remove files. Here I can navigate to the file. So inside this, if you could see, this is the full adder behavioral 4-bit code which I'm going to open, and then I'm going to add another file that is a simulation. This is a test bench file that I have created for behavioral 4-bit. It is here. I'll just import this and yeah, I'll click apply and then OK. Now if you see, both the files have been added successfully. This is the 4-bit and this one. So since I'm not using these two, I can just remove this from the project folder itself. So I can make this as a top level entity. I can then compile. So this is the code for 4-bit. So if you could see, these are the 4 bits for A and B, and then for sum we have, and then the workflow, that is a carry. This is C in, that is carry in. So now if you see, the compilation has been successful. You can see the message here, full compilation was successful with 0 errors and 15 warnings. So let's try to read the reports. Yeah, if you can see, we have used 3 ALMs and we have used a total of 14 pins. And if you can see the resource utilization, we have used 5 ALUTs. So let me show you the timing part for this. Okay, I've already run this. So I'll open the timing analyzer. So yeah, if you see here, I have to go to custom reports and then I'll report the path. So this will give us the critical path for the circuit. So that's the longest path it's taking from the input to output side. I'll click on report path, and if you could see, it's from A of 0 to S of 2. So this is the critical path and the delay is 8.070. So inverse of this will get the maximum frequency of the circuit. So that's the allowed range for the circuit to work properly. How you can do it for structural Verilog 4-bit. I'll remove these projects and then I'll go to files, add or remove files, and then I'll navigate to the folder. I'll select this file, that is a design file, and then I'll select the test bench that I have written for structural 4-bit. I'll click apply, I'll click OK. So if you could see, this is the structural Verilog for 4-bit adder. So I have a module created for a single bit and then I'm cascading the module for the 4 bits also. So if you could see, this is the test bench code. This is the test bench code for that design. So I'm gonna compile this now. So I'll set this as a top level entity. Just a minute, I'll go into the hierarchy, the files, and then I'll set this as top level entity, and then I'll compile. So now I have compiled the file successfully. If you could see the report, I'm gonna click on view report. Flow summary. So the ALMs used are 4, and if you see the resource utilization, we have used the total of 6 ALUTs and 3 ALMs. ALUTs are 6. So let me show you the timing analyzer. So I'll click on report path to get the critical path. I'll just start this. So I'll click on report path. So this is the delay for the structural, that is 7.868, and it's from B to C out.